class. Today we'll be looking at Chapter 5, Number Theory in the Real Number System. Today we will be looking at the rational numbers in 5.3. We will be working halfway through Section 5.3 and will complete Chapter 5.3 in the next lecture. We're going to break it into two pieces. We're going to look at, in 5.3, for our objectives, we're going to define the rational numbers, reduce rational numbers, convert between mixed numbers and improper fractions, express rational numbers as decimals, express decimals in the form A over B, multiply and divide rational numbers, add and subtract rational numbers, use the order of operations agreement with rational numbers, apply the density property of rational numbers, solve problems using or involving rational numbers. As you can see, we have a lot of objectives this chapter, which is why we're going to break it into two manageable pieces. Let's start by defining the rational numbers. The set of rational numbers is the set of all numbers which can be expressed in the form A over B, where A and B are integers and B is not equal to 0. The integer A is called the numerator. The integer B is called the denominator. The following are examples of rational numbers: 1/4, -1/2, 3/4, 5, and 0. Now it may be easy to see that these first three here fit the definition of rational number because most rational numbers are written here as fractions. But we can indeed write 5 as a fraction as well, 5 over 1. And we can also write 0 as a fraction. 0 over any number is a fraction. So even 0 over 1 is a fraction. So these are as well rational numbers. Any number that can be written as a fraction, either positive or negative, is a rational number. If A over B is a rational number and C is any number other than 0, then A times C over B times C is the same thing as A over B. Essentially here, these C's just cancel themselves out. The rational numbers A over B and AC over BC are called equivalent fractions. So we're going to begin looking at fractions and possibly reducing fractions. In order to reduce a rational number to its lowest terms, we need to divide both the numerator and denominator by their greatest common divisor. Now we've gone over greatest common divisor. Let's look here and see and practice reducing using the greatest common divisor. We want to reduce 130 over 455 to the lowest terms. Our solution, we will begin by finding the greatest common divisor or the greatest common factor, same thing, of 130 and 455. In order to do this, we will look at the factors of 130, broken all the way down to its prime factorization. We look at two numbers that go into 130. Here we broke it down into 2 and 65. Then we further broke 65 down into 5 and 13. 5 and 13 were both themselves prime, so we couldn't break it down any further. We look at 455. We broke it down into 5 times 91, and 91 was able to be further broken down into 7 times 13. So if we wrote their prime factorizations out, 130 is 2 times 5 times 13, and 455 is 5 times 7 times 13. So if we look at it, the greatest common divisor, remember, is what they have common between both of them. In this case, it's a 5. Ooh. Let me get my pen working. In this case, it's a 5 and a 13. 5 times 13 is their greatest common divisor, or if we multiply that out, we see their greatest common divisor is 65. So we know their greatest common divisor now. We're not done. What we're going to do here is, we've got it two ways. We can divide the numerator and the denominator of the given rational number by 5 times 13 or by 65. In this first number here, or in this first case, what I do is I write out their prime factorizations instead of the number. So here the prime factorization of 130 was 2 times 5 times 13. I write that up top. The prime factorization of 455 was 5 times 7 times 13. And I notice here that this 5 cancels with this 5. This 13 cancels with this 13. And I'm simply left with 2 over 7. Now if you don't like doing it that way, you could recognize that 65 is their greatest common divisor. And so we could divide 130 by 65. That would leave us the 2. And we could divide 455 by 65, and that would leave us with 7, which would leave us in our most reduced form of 2 over 7. There are no common divisors of 2 and 7 other than 1. Thus, the rational number 2 over 7 is now in its lowest terms. Let's look at mixed numbers and improper fractions. A mixed number consists of the sum of an integer and a rational number expressed without the use of an addition sign. Example, 3 and 4/5. The integer 3 and the rational number 4/5, written as 3 and 4/5, means 3 plus 4/5. An improper fraction is a rational number whose numerator is greater than its denominator. So if you hear the term improper fraction, that means the numerator is greater than the denominator. Our example here is 19 over 5. This is an improper fraction because 19 is bigger than 5. So we can represent this in basically 2 ways here. These are actually the same number represented. Here it's represented as a mixed number. Here it's the same number represented as an improper fraction. Let's look at converting a positive mixed number into an improper fraction. In order to convert a positive mixed number into an improper fraction, we need to multiply the denominator of the rational number by the integer and add the numerator to this product. Place the sum in step 1 over the denominator of the mixed number. So let's look at this example and prove that those two numbers that I said were the same are actually the same. We want to convert 3 and 4/5 to an improper fraction. Essentially what you're doing here is 3 and 4/5 is the same thing as 3 plus 4/5. You're essentially finding a common denominator here, if you've done that before. The common denominator would be 5. In order to put this 3 into terms where it has a 5 as the denominator, I need to do 5 times 3, which is 15. 15 plus 4 is 19. Now written another way, we have 3 and 4/5. If we want to write that as one fraction, that's 5 times 3 plus 4. 5 times 3 plus 4. 5 times 3 is 15. 15 plus 4 is 19. We wind up with 19 over 5. It says multiply the denominator by the integer, add the numerator, place the sum over the mixed numbers denominator. So you can either do it the way I showed up here, or you could do it the way that it showed down here in the book solution. Let's look at converting a positive improper fraction to a mixed number. In order to do this, we are going to divide the denominator into the numerator. We are going to record the quotient and the remainder. We are going to write the mixed number using the following form. Quotient first, remainder over original denominator second. Your quotient part will be your integer part. Your remainder over original denominator will be the rational number part. So let's convert 42 over 5 to a mixed number. We look at our solution here. Step 1 is to divide the denominator by the numerator. We actually have to do a division here. Now this division is done for you here, but maybe it'll be easier to see if it's done step by step to practice your step by step by hand division. If I divide 5 into 42, 5 does not go into 4, but 5 does go into 42. If 5 goes into 42 8 times. 5 times 8 is 40. So that's what I'm taking away from 42. 5 does not go into 2. We're not looking to have decimals here. We're okay with this remainder, as you see here, of 2. Because what we're going to do is take this quotient, which is your 8. That is going to be our integer number out front. So our quotient here, we put it out front. We put the remainder back on top of the 5, which is our original denominator. So step 2 says write the mixed number using the quotient, remainder over denominator. Thus, 42 over 5 equals your quotient, which we found to be 8. And then you write your remainder, which was 2, over your original denominator, which was 5. Rational numbers and decimals. Any rational number can be expressed as a decimal by dividing the denominator into the numerator. So let's express each rational number as a decimal. Solution. In each case, divide the denominator into the numerator. Let's do this. A says 5/8. B says 7/11. If I look at dividing 8 into 5, because my original problem here was 5 over 8, I could do this division. 8 does not go into 5, so I place a 0. I keep the decimal in the same location. I just pull it up. I'm now looking at dividing 8 into 50. 8 will get as close to 50 by multiplying by 6. 8 times 6 is 48. So I put my 6 up top. I do 50 minus 48 is 2. I bring down my 0 here. So now I'm dividing 8 into 20. The closest I can get is 16. 8 times 2 is 16. So I put my 2 up top. Put my 16 down here. Subtract. That's what I'm doing here is subtraction. I'm subtracting 16 from 20. That gives me this 4. And then I bring down a 0 here. I'm looking at I'm looking at now 40 here. 8 goes into 40 5 times because 8 times 5 is 40, which gives me an overall subtraction here of 0, which means that my final answer here, 5/8 written as a decimal, is 0.25. Now, that turned out very, very nice here. Okay, it turned out to wind up being a terminating decimal. So the decimal ended here because we wound up with a 0 remainder. However, it says right here, notice this decimal stops. This is called a terminating decimal. However, we can have a scenario where this decimal does not terminate. Here, if we divide 11 into 7, because our original fraction was 7 over 11, if we do this division, what we see is 11 does not go into 7, but 11 does go into 7D. The closest we can get there is a 6. So 11 times 6 is 66. We subtract that. We see, okay, I have 4 remainder. I pull a 0 down. 11 goes into 40 3 times. I do 40 minus 33 because 11 times 3 is 33. 40 minus 33 is 7. I bring a 0 down. And what I can see is I wind up with a pattern starting to emerge because I'm back at 70 now. And 11 goes into 70 6 times. But if I do 70 minus 6 here, or 66 here, I'm left with 40, which is what we had before. I continue to bring zeros down, and I have this recurring pattern of 6 3 6 3 6 3. Notice the digit 63 repeat over and over indefinitely. This is called a repeating decimal. What we notice with rational numbers is rational numbers can all be written as fractions. If you have a fraction, then you have a rational number. If you're looking at just the decimal representation, as long as that decimal terminates or repeats, that decimal can be written as a rational number. So, it says terminating decimals can be expressed with denominators of 10, 100, 1000, 10,000, and so on. Using the chart, the digits to the right of the decimal point are the numerator of the rational number. So we see we have stuff in the tens place, the ones place, and then we have a decimal point here. And then we go to the tenths, hundredths, thousandths, 10,000ths, 100,000ths, and we can continue on if we would like. We want to express each terminating decimal as a quotient of integers. Okay. What we see here is because in A, the 7 lies in the tenths place. In order to write this terminating decimal as a fraction, I need to put 7 over the 10 because the 7 is in the tenths position. The 49 is in the hundredths position. So because the 49 is in the hundredths position, I need to write it as 49 over 100. Okay. The specific digit that is in the hundredths position is the last digit, and that is the digit we are truly concerned with when we're looking at this. We also had C, which was 0.48. In order to write it as a fraction, the 8, the last digit here in my decimal, it's in the tenths, hundredths, thousandths. It's in the thousandths position. So we need to put 48 over 1,000. But unlike the two previous answers in A and B, A was 7 over 10. 7 over 10 does not reduce. So we were at a complete reduction there in lowest terms. 49 over 10 or 49 over 100 also does not reduce. So we were at a complete reduction there in lowest terms. However, 48 over 1,000 can be reduced. And if it can be reduced, we do need to lower it to its lowest terms. What we see here is that the greatest common divisor or greatest common factor here of 48 and 1,000 is 8. So if I do a simple division by 8 of 48 and 1,000, it reduces it to its lowest terms of 6 over 125. Be sure to reduce stuff to lowest terms. What we next need to look at is expressing repeating decimals. Okay, so we want to express 0.6 repeating as a quotient of integers. I got a little bit of a process here now. Step 1, we need to let n equal the repeating decimal such that n equals 0.6 repeating, or 0.6666666 repeating. Step 2, if there is one repeating digit, multiply both sides of the equation in step 1 by 10. Okay, so here we have an equation n equals 0.6 repeating. If I multiply both sides of the equation by 10 here, I see that I have 10 times n equals 10 times 0.6 repeating. But if I simplify that, that means I have 10 times n equals 6.6666 repeating. Multiplying by 10 moves the decimal place one place to the right. Step 3, I need to subtract the equation in step 1 from the equation in step 2. Okay, so if I do this, what I see is that I have 10n equals 6.6666, and if I subtract the second equation from it, the n equals 0.666 from the first equation. 10 minus n gives me 9n. 6.666 minus 0.6666 just leaves me with the 6 here. I divide both sides of the equation in step 3 by the number in front of n and then solve for n. So we solve 9n equals 6 for n by dividing by 9 here, and that gives us our repeating decimal in fraction form. So here I did 9n divided by 9 equals 6 over 9. Therefore, n equals 6 over 9. I still have to put it in lowest terms. 6 over 9 in lowest terms is 2/3 if you divide 6 and 9 both by 3, which is their greatest common divisor or greatest common factor. This completes our first half of chapter 5.3. Please come back next time and we will continue on with multiplying rational numbers and the rest of the lecture. You can go ahead and begin to attempt some of the homework problems with Chapter 5.3. The ones that don't look familiar will be covered in the next lecture. You will have time to learn and complete those. If you have any questions, please don't hesitate to reach out by email, and I'll get back to you as soon as possible. I hope you have a good rest of your day.